Hey guys, Buildzoid here, and today we're going to be doing some Intel DDR5 overclocking. The idea behind this video is very simple. I wanted to show that you don't need a high-end DDR5 memory kit in order to get good memory overclocks with an Intel CPU. So the hardware configuration that I've gone with here is admittedly a little bit memory-centric, but not like ridiculously expensive. So we're on the 13600K because the 13600K has a better memory controller than my 13900K, but it's also not the 13900KS because I don't think the 13900KS is a very realistic CPU. Or a very sensible CPU. It's very expensive. Like, in my opinion, Intel's like sweet spot CPU would be the 13700K, but I don't have one, and I can't justify buying one just for the sake of a couple videos. So yeah, 13600K it'll like 13600K it is. And there's the MSI Z790i Edge, which is the memory-centric part of this system setup because it's an ITX motherboard. And honestly, it has a good feature set. Voltage regulation is good. VRM thermals are, well, it doesn't like the 13900K, but if you have airflow over the board, they're fine. If you don't have airflow, they're not fine. Yeah, because it's an ITX board. There's just not enough space for big enough heat sinks or a big enough PCB to dissipate the heat on its own. Like the VRM, like the thing is, the VRM components MSI is using are good. It's just the thermal density is too high because it's an ITX board. But anyway, but the main thing, it's an ITX board. It has a 1 DIMM per channel memory topology. So this board's actually a very good memory overclocker. I wouldn't say it's the best memory overclocker. In my experience, it works well up to like 7600, and then past 7600, things get very, very, very difficult very, very quickly. We're probably not going to reach speeds that high because the memory kit that I went with is a Hynix MDI based kit, and this is entirely random because basically the way I ended up with this memory kit is when I was ordering the direct die frame, I wanted to pick up a normie memory kit. So my choices were this 6000 CL36 kit or like a 5600 CL36 kit from Kingston, both of which are probably going to be Hynix memory chips, but the 6000 CL36 kit was cheaper at the time that I was making the purchase, like it was on a slight discount. So I went with the 6000 CL36 kit, and yeah, this is in my opinion, very normal memory kit, right? Like it's just 6000 CL36, it has an Expo profile, it has an XMP profile, it's single rank, it's Hynix MDI, which is the only part that I'm kind of disappointed about. I was really hoping to get lucky and get an A-die kit, which can happen. Like, I've seen G-Skill 6000 rated kits come with A-die. I think I've even seen some 5600 rated G-Skill kits come with A-die. But yeah, as far as I can tell, it's pretty random as to what you're actually going to end up with, and this ended up being a M-die kit. So if you definitely, like, if you wanted a higher probability of A-die or like a guaranteed A-die kit, you'd have to buy at least a 6800 rated kit instead of like a 6000 or a 6600, but 6600 is a speed that you don't, like, that's not a very common speed. Like, the memory kits tend to go in, like, increments of 400, so you've got your 6000, your 6400, then your 6800, and then 7200, and, well, by the time you get to 7200, the kits get very expensive. Anyway, yeah, so we've got an M-die kit instead of an A-die kit, so that will probably limit the max memory clock that we can reach. But I haven't done any pre-testing because I wanted to show you sort of the full process of overclocking some DDR5 with an Intel CPU. And on admittedly, like, a better than average, well, on a 1 DIMM per channel motherboard. Like, as far as I'm concerned, if your motherboard has 4 DIMM slots, you can't even begin to compare it to an ITX board. So, yeah. Anyway, let's get into it. I've cleared the CMOS, and the first thing I will be doing is showing you, well, first we're going to enable the XMP profile, check the stock performance. We're also going to disable the E-cores because they get in the way when doing memory overclocking. Especially with some of the stress tests, they just don't work properly. And technically, you can go into Windows and manually fix the E-core compatibility, but like I don't feel like dealing with that. So, yeah, I mean, you can turn them back on after you have all of your memory stress testing done. Probably. Anyway, so we're going to go into the BIOS. And it first asks us, we're just going to use the no limits, and we're going to just immediately enable the XMP profile, and we're also going to disable the E-cores. Because, where is it? Yeah, so XMP profile, and we're just going to turn that on. And then we're going to go over here, and goodbye E-cores. No more Cinebench acceleration for this CPU. Anyway, I'm going to put the system specs out of the way at this point. You can see that I do have a fan for like cooling the motherboard and the memory sticks. Also, there are troubleshooting LEDs over here that are color-coded. So, yeah. The board doesn't have a postcode, but it's an ITX board, so what do you expect? Right, we're going to keep the memory kit spec in the frame. This is normal. I think the OS install that I'm using is like not UEFI compatible, so the double post after a clear CMOS is normal. Or is it? I'm not sure. I'm like, the thing is, I have like a bunch of different Windows installs, and some of them are, well, yeah, this one just double posts on every modern motherboard. Anyway, so here we are in the OS, and we're going to run a few, I guess we're going to start with IDA, even though it's not, like, I don't like IDA, because it's very synthetic, and the problem with your very, very synthetic memory benchmarks is that they can be affected by things like the architecture of the CPU, which is like, well, that's not good, okay? If you have to tailor your software to, like, work, like, or if you have to tailor your benchmark to work correctly based on the architecture, I don't like that. Because it's like, from a real-world perspective, like, you're not trying to measure the memory latency. Right, if you have some kind of memory latency intensive workload, you're not trying to measure the memory latency. You're just running a calculation that happens to be memory latency intensive. So, yeah, I don't particularly like super synthetic memory benchmarks, but because they are very popular, I figured, you know, just for like normie purposes, we're going to run IDA. It's also worth noting that the read, write, and copy bandwidth are affected by how many cores you have active, so if the E-cores were turned on, those would be higher. So we're getting like 70-ish nanoseconds of latency, which I guess is expected for an XMP profile. To be completely honest, well, no, like I said, I literally do not have a normal XMP memory kit, so... okay, so now we're getting like 68 nanoseconds. Actually, I'm just going to rerun the whole batch. Because the thing is, this Windows install is a bit old and messed up at this point, and so the first couple seconds after it starts up, it doesn't tend to score quite right. You might be wondering why I haven't gotten rid of it at this point, and it's like, I'm too lazy. And mostly I use this Windows install for, like, running memory stress tests, so yeah. Anyway, so we are hovering somewhere between like 68 nanoseconds and 70 nanoseconds, which I'll take that. 87 gigabytes read, and like 83 write, 83 copy. Cool. By the end of this, we should be well, actually, I don't know if we're going to be over 100 gigabytes per second. We might, but this is MDI, so I can't rely on just clocking it through the roof. Anyway, now we're going to run benchmarks that I do care about, the benchmarks that I use to check if IDA is lying or not, because that's one of the issues with your synthetic memory benchmarks. It's just like sometimes they spit out numbers that don't look quite right, and then you need to go run something that's actually trying to do some kind of calculation to verify whether or not that synthetic benchmark is just bugged out or not. Anyway, PyPrime is spitting out 10.5 seconds-ish. By the end of this, I think we will be well under 10 seconds. We might be in the 9s. But yeah, so 10.5, and we're also going to run Y-Cruncher. We're not running these multiple times because the difference between the XMP profile and the settings that we're going to end up with is going to be so big that I don't really see a reason to run these multiple times. Like, the run-to-run variance is going to be completely irrelevant compared to what an improvement the manual timings are going to make. Anyway, and Y-Cruncher runs in about 33.4 seconds, or 33.3 seconds, whichever you prefer. We're going to be, well, actually, I'm not sure how low Y-Cruncher is going to get, but we'll see. Anyway, now for the Hynix M-Die test. So the easy way to test if you have Hynix A-Die or M-Die, if you know that you have a Hynix memory kit, is this timing right here. If you can set it to 300 or lower, or actually, I think it's even if you can set it below 400, basically, but I'm actually not sure what, like, minimum TRFC on A-Die is. But on M-Die, you can set TRFC very, very low. So, yeah, if you punched in a TRFC of, like, 266 on a A-Die memory kit, it would just immediately lock up. Like, the system would immediately crash. We can also do this, and that's completely fine. So, you know, yeah, this is a M-Die memory kit because we can run very low refresh cycle timings. If it was an A-Die kit, this would not work. Anyway, now we're just going to restart, and we're going to start actually overclocking. So the first thing we want to do is sort of, well, I want to see if 1T command rate is at all viable. I want to check that. 1T command rate with DDR5 is a bit weird in the sense that, like, sometimes it doesn't work at all. On some, like, depending on the BIOS, it might not work at all. Also, we're going to disable one of these training options, which is, where is it? Late command training. This, on some motherboards, is actually disabled by default because all it does is it makes it less likely for you to post after adjusting memory settings, especially at high memory clocks. And it does absolutely nothing for stability, in my experience. So, especially on gigabyte boards, if your gigabyte board has a post code and it goes like 3E54, it's failing late command training, and you can just disable it, and it won't make a difference to the stability because I don't actually know what late command training is trying to do, but it doesn't help. So, yeah. Anyway, we're gonna set command rate to, well, command stretch to 1, and we're not gonna touch anything else just yet. We're just gonna see if that works. Because the reason I want to know if that's going to be at all viable is because with M-Die, we probably won't be able to run high clocks, which doesn't necessarily mean that we're going to be able to run 1T command rate at any reasonable clock speed either, but it would be nice if we could, like, if we had, say, 7000 1T, that would be pretty good. If we get stuck at, like, 6400 1T, I think I'm going to ditch 1T command rate, and we're going to go for 2T. Anyway, it looks like the board has no problem posting 1T command rate at 6000. Basically, the way I see 1T command rate is like it's a crutch you can lean on if your memory clock doesn't go high enough. If you're lucky. Because it in and of itself will actually cost you some amount of memory clock. We're just going to put this to gear 2 so that, yeah, it pulls out. Because the thing is, if we leave the board on auto, you'll see that we have like gear 4 options in the DRAM frequency configuration, which we don't want because gear 4 is terrible. Also, I think on this BIOS it doesn't even work, so it wouldn't even post. Anyway, so we're gonna put it to gear 2. Actually, initially I don't. Well, am I not gonna touch the voltages? And we're gonna go to 1.45 volts, which is like. Yeah, we're going to go straight to 1.45 volts on the memory voltages because, I mean, I have a fan pointed at the memory sticks. Also, actually, 1.45 volts, as long as you don't push your refresh timings too hard, you can actually still run it at, like without direct airflow. Anyway, and we are going to check that it still posts, because the most annoying thing about DDR5 is that it has a lot of signal integrity issues, which basically means that just because you raise the voltage doesn't necessarily mean the stability is going to improve. In fact, in a lot of scenarios, raising a voltage can cause more problems than it fixes. And the consequence of that is that pretty much every voltage related to like DDR5 overclocking, especially once you push the speeds high enough, ends up having a sweet spot that is very specific, and that makes life very annoying. Because if you're off by like 50 millivolts, the system doesn't post. And when I say off by 50 millivolts, I mean you could be 50 millivolts too high, you could be 50 millivolts too low. And technically, you could probably find sweet spots that are even more specific than that, but I think if your memory overclock is within 10 millivolts of not being stable, you probably shouldn't be dailying it. That just doesn't seem like a good idea. Okay, so 1.45 volts hasn't caused any immediate issues, so the next step, we're going to loosen out the TRCD timings. Well, actually, we're just only going to loosen out TRCD. It's like TRCD itself. And the reason for this is that generally speaking, if you're going to push memory clocks, TRCD is sort of the main timing that's going to limit you, and also TRP. And we're going to leave the rest alone because they don't actually do anything. We could actually drop TRCDW to like something very low. I have a video on why you can set incredibly low TRCDW. I'm not going to get into it right now. Anyway, so we're going to save and reset. Also, it's worth noting that TRCDW doesn't really affect your performance very much in real-world applications, because under most circumstances, your CPU's performance is not going to be write-limited, it's going to be read-limited, in the sense that you probably need to read a lot more data than you're going to be writing, right? Most of your calculations, things go in to get calculated and then output, so you often need more inputs than you have outputs. And so generally speaking, you're going to be read limited rather than write limited. And so write timings don't tend to have huge impact on benchmarks. Even though on a lot of memory chips, they can get very, very low. Anyway, so that works. And now we're going to go up to, I'm just going to go straight to 6400. I don't see any reason why to go any, like, testing 6200 is pointless. Like, the thing with memory overclocking is you want to get to things that don't work quickly. You want to see errors quickly. You don't want to be, like, well, this is difficult. Because on one hand, you don't really want to be, like, stress testing a bunch of settings that are stable, because that's a waste of time, right? If you stress test something that's stable, it's like, okay, so I just spent 12 hours running stress tests to make zero progress because we're going to ditch all of those settings and we're going to increase our frequencies. So we've just wasted a bunch of time running stress tests on settings that we're not actually going to be running. Right? And so, yeah, anyway, we're going to go for 6800. Now, if we can get 6800 1T to work, I would be impressed. Like, that would be a good result in my book. If we could go higher than 6800, though, that would be ideal. And the thing with Hynix MDI is it can do very high speeds. But it's kind of motherboard dependent, because it's a lot harder to run than ADI is. Okay, so it looks like we're already having some post issues. Yeah. This board's auto recovery is pretty good, so I shouldn't have to hit the clear CMOS button. Or at least I hope it's pretty good. Like, I've done a decent amount of memory overclocking with this board, but it was like a month ago, so okay, I think we hit the auto recovery. So now what we're going to do is we're going to set 2T command, right? I guess we could try like 6600 1T, but the thing is, if we can just outclock the 1T penalty, then, or like the 2T penalty, then it's worth it. And I keep saying 2T even though it says 2N, but same thing. Well, Actually, I think on a very technical level, it's not the same thing, but close enough. Okay, that posts. So next we're going to go for 7,000. And the reason we're going to stop at, like, we're slowing down the increments now is because, well, I'm not even sure 7,000, like, I would not be too surprised if 7,000 didn't work. Yeah. Though I'm hoping it does. Okay. So 7,000 posts. Depending on the board, like, we might see even, like, like, I'd be really happy if we hit 7,400, is sort of what I would be very pleased with. I'm going to try the 7,200 there. Also, if you're wondering about the different ratio options that you have for the various memory frequencies, they don't really make a difference most of the time. You might find in some situations that, like, one ratio combination is more stable than another, but like, I've not really run into that with DDR5 too much. It used to be like on DDR4 Intel CPUs, the 100 based ratios were really not great in terms of stability. Like, a lot of the time, like 4133 would work, and then 4200 wouldn't, and 4266 would work. So you'd have like the 133 ratios being better, whereas the 100 based ratio is not. But yeah, I've not encountered that with DDR5, so that's not too much of a concern. So 7200 works. I am impressed. Then again, this is an MSI motherboard, so I guess I shouldn't be too surprised. MSI generally has, like, the most flexible memory support in my experience compared to a lot of other motherboard vendors. As in, like, you can sort of throw any memory chip at an MSI motherboard and it'll probably work. As long as the memory chip isn't so new that, like, there isn't any BIOS support for it just yet, but yeah. Whereas some other motherboard manufacturers have a real issue of, like, their BIOS being tuned for, like, one very specific, or, well, for, like, a few very specific kits of memory or memory chips, and then it gets really annoying where it's like, oh yeah, the motherboard is amazing as long as you only use the memory that the manufacturer sort of optimized it for. Whereas MSI seems to optimize for just anything. And we're posting 7,400. I am impressed. I want to know, like, going into this, I was worried that, like, this wouldn't work. And also at this point, we should probably loosen out the TRCD again. Yeah, okay, so are we gonna, yeah, let's try 7466. At this point, I kind of feel like we're gonna have to run Y-Cruncher just to see if it immediately crashes, because the most annoying thing about the 13th gen memory controller is its ability to initialize memory settings that are completely unrunnable. Which means you can, like, for example, you can run, say, Pi Prime, because that's a very, very light memory benchmark in terms of how hard it is on stability. You can run that at, like, some crazy speeds. But then when you try to run something like an actual memory stress test, you'll find that you need to drop like 800 megabits per second before you have stability. So yeah, I wouldn't necessarily be too surprised if we didn't manage to even get into Windows at this speed, but evidently this board is very good with MDI, because we are on the desktop and it hasn't blue screened yet. I was not expecting that. Because I did briefly test this memory kit on a different motherboard and I couldn't get it above 7000 there. Because I'm pretty sure that motherboard is designed for like A-die and A-die only, and so you try to run M-die on it and it doesn't work. Huh. Looks like MSI is automatically bumping our TREFI up, which I'm not going to complain about that. That is generally a good idea, especially since they're only bumping it up to like 32,000. That's not going to affect stability in any way, shape, or form. We're going to try to run Y-Cruncher, because this is very heavy. So... And it's not the heaviest. There's an even heavier configuration. Well, so this is the Y-Cruncher benchmark, but there's Y-Cruncher has a stress test mode, which is so much harder. So yeah, that like especially on Intel CPUs, it's just incredibly hard on the memory controller. And so we are going to also check that because I have my doubts about like this being a good idea. Okay, so we shaved off half a second already. 32.9 instead of 33.4. Not as much of an improvement as you'd hope for. I guess let's quickly run PyPrime, but then we're going to hit Y-Cruncher VST, and also we're going to need hardware info for that. Oh yeah, so PyPrime is just way, way faster. This benchmark is crazy in terms of how memory sensitive it is. Yeah. Like, we're already at 8 seconds. And I guess at this point we could also run IDA, just cause. There we go. Come on. Cache and memory. Yeah, so we're over 100 gigabytes per second. And this is the thing, like, you don't need a high-end memory kit to hit high-end speeds. You just need a good CPU, a good motherboard, and a good BIOS, and a fan. Actually, I don't think the fan is really... Like, just for what we're doing right now, the fan I don't think is really making a difference. The fan makes a difference if you're running a stress test for extended periods of time. We are getting 55 nanoseconds of latency. That is way better than I expected for, like, what? Not even half an hour of tuning. So, yeah. No, go away. We want hardware info. Because the thing is, we're going to hit Y-Cruncher VST, and I'm going to quickly show you the options. Oh, wait, no, it's not the memory. Where's my memory? There. Yeah. So this is Y-Cruncher stress test mode. Test length is 3,666 seconds, and the stress test is VST, which is like a... well, it's very, very harsh on the memory. Also on the cores, if you have enough memory bandwidth, like it runs pretty hot, but we will see. So we're going to start that, and hopefully it doesn't instantly crash. If it does, which wouldn't necessarily surprise me. Oh, it doesn't. That's surprising. That's actually really... Yeah, that is very surprising. I'm very used to this test. Like, well, okay, usually it's above 7600, but that's with A-die kits. So I didn't think like an M-die kit would get anywhere near what like A-die kits do for VST, but I mean, definitely too early to celebrate. There's a reason why the batch file is set to run for an hour. But yeah, the fact that it just hasn't immediately died is like, that's a good sign. Because this is really hard on the memory controller. So, oh, there he goes. Yeah. Yep, that's Y-Cruncher. Okay, so that lasted not even a minute. That's honestly better than I was expecting. We're gonna see if like 7600 gets it to the point where it just immediately falls over. Which it probably will. But, yeah, so I think we're probably... I think we're going to just back off to like 7200. Because the thing with the memory speed is just like, it's very... I mean, we could also just back off to like 7400 and it might be enough to clean it up, but... well... Actually, it might, because the thing is, Y-Cruncher VST breaks like really hard, really fast. As in, like, on a motherboard where, like, if you have settings that work at, like, 8000, if you clock them to, like, 8100, they stop working, potentially. Again, depending on the motherboard. So, yeah. Like, it is actually possible that, like, 7400 would work and 7466 doesn't. At the same time, I would like to point out the fact that 7200 and 7600 are, like, not that far apart. And let me just pull up the calculator for that. So, if we take 74, like, well, yeah, let's say 7600, which just posted. So, yeah, this motherboard is very good at booting high memory speeds. That's a difference of 5%. Right, and that's not accounting for the fact that, like, your timings get slightly looser as you go up in speed. So you're not even going to see, like, at best, in a 100% memory bandwidth limited workload, going from 7200 with the exact same timings to 7600, you would see a 5% increase in performance, assuming your workload is 100% memory bandwidth limited. That's not realistic at all. And so this is one of those things with the with like overclocking a Intel CPU or like overclocking memory on really any CPU. Don't, bend over backwards to get a speed working that gives you a 5% increase in performance, like a theoretical 5% increase in performance that realistically you're never going to see, because most workloads are not 100% memory bandwidth limited. And anyway, the board does boot 7600, which I gotta say I am very impressed by. I was really not expecting that to work. That's cool. Though I think at this point, if we try to run VST... Well, we're not going to start with VST. We're first going to try Y-Cruncher benchmark. And then we're going to try VST. Because the benchmark... Okay, yeah, so... Okay, VST doesn't have a chance. The benchmark's falling over at this point. I do wonder what Ida thinks of this. Might be, at this point, maybe, like, loosening out the timings. And the thing is, we can actually adjust those timings in the OS, and that will work. Six. I mean, the cast latency isn't that low. So actually, we're going to try Y-Cruncher again. I don't think it's going to fix it. The thing is, in my experience, it's usually... Like, usually the problem with stability on the Intel CPUs, it's like, it's not the timings, it's signal quality issues. And that means you get to sit there fiddling with voltages for days, and it probably still errors out. So, depending on how far you push the speed. So, yeah, okay, so this is just not going to work for Y-Cruncher at this point. So this is definitely not stable. I do still kind of wonder, like, is this... will it still be, like, can we go higher? Like, obviously it's not stable at this point, and I think, if like, how... I don't even know if it's possible to stabilize it at this point. Like, that's the biggest issue, is, like, I don't know. I have no idea. It might not be possible. Yeah, but I do kind of wonder, like, hey, could we get a screenshot of DDR5-8000 with this kit? Because, like, this is a 6000 rated kit, so... We're just gonna YOLO to DDR5-8000 right off the bat. We're probably gonna need... Actually, 1.45 volts might be enough, but we're gonna have to loosen out the timings again. I'm gonna... 38, 48... Actually, yeah, like that. And with any luck, it'll post. Or we'll hit the auto recovery. Okay, I think it's gonna hit the... wait. Oh, it's not flicking back to the... Yeah, okay, so it might actually post. Damn. That's impressive. And this, like, but at the same time, like, already at 7600, this doesn't work, right? Like, so, I don't know, we might get into Windows, we might get okay, we might not even get into Windows. But yeah, already at 7600, this is very unstable. So even if it posted DDR5-8000, I think it would be well into the territory of, like, this is never gonna work. Okay, I think it'll hit the auto recovery pretty soon. So I think like a realistic speed for this, we could also try like 7333, but again, like, you know, I'm just gonna bring up the, like, because there is a 7333 ratio which works as far as I know, like, but like it literally, like, you could just, it's the same thing as 7200, right? Like, that's 1.8%. Literally doesn't matter. And again, like, as the higher you push the speed, especially if, like, you can always tell yourself, oh, it's just a 5% overclock, it's not going to be unstable, and then it isn't stable. So it's like, no, that's not how it works. Like, at a certain point, the frequency is just too damn high. So, okay, so 8000 won't work, and 7800 isn't screenshot worthy, so we're just gonna drop down to, well, 7466 already didn't like Y-Cruncher very much. Oh wait, there isn't a 7333 ratio. So yeah, we're actually gonna go to 7200. I see, like, because the thing is, like, I really don't feel like spending hours and hours and hours trying to get 7466 to work for a 4% performance improvement. Over 7200. Whereas 7200 is like, that should be very doable with this motherboard. And so that's what we're going to go for. Probably like 34 instead. Actually, well, so the only one we can't tune in the OS is the cast latency. You have to boot your cast latency, because the cast latency actually has to be set on the memory stick as well as the CPU's memory controller. Because, like, for example, TRCD, this controls the activate to, like, read/write command timing. And the thing is, your memory stick doesn't actually need to know what TRCD is. Like, the memory stick doesn't need to, yeah, literally, the memory stick does not need to know what TRCD you have set. The memory controller needs to know what the TRCD is, because the memory controller sends the activate command, and then after TRCD cycles, it sends a read or a write command. But the memory stick doesn't need to know when the read command is going to show up after a write command. It's just going to get a read command eventually, and either there was enough of a delay between the activate and the read, and you get valid data back, or there wasn't, and you get a bunch of garbage. So anyway, we can tune that in the OS. We can also, actually, we can't adjust TRCDWR for whatever reason. Even though that's also controlled by the memory controller. Really not sure about why that is. Anyway, we're going to set that to 16. 44 TRAS, we're going to go to like 40. Actually, this is MDI, so we can set it very low. Sure, let's go to the register limit. I don't see any reason to be sensible about this. 333 per bank 222, and then 50,000 refresh interval. The thing with the refresh interval is, once your refresh interval is more than, like, well, so the way the refresh, so yeah, basically once your refresh interval is more than like 100 times your TRFC timing, you don't really see much of a performance improvement. So, and the reason for that is, like, with a TRFC of 333, if we had a refresh interval of 33,300, 1% of our available memory clock cycles would be used up on refreshing. And if we went from like 33,000 to say 66,000, then like 0.5% of our available clock cycles would be spent on refreshing, which just doesn't make that much of a difference to performance. So we don't have to worry about that. TWR isn't real. WTRL also isn't real, as in these are literally not registers on, actually, this is MDI. Oh yeah, we can go 4.4. It's MDI. RTP, wait. So, Oh, whoa, MSI is setting this really low on auto. Oh, wait, we're at JDEC right now. Oh, well. Actually, we probably want like 14.8 at 7200. 64. Yeah, that seems sensible. And then these, actually, so the thing is, these generally don't go much lower than like, well, I don't know, at 7200 they might do 18, but on auto I think they'll end up at 20 anyway, so like 18 and 20 are pretty much the same thing. You know, if you squint hard enough. Anyway, down here we have write to precharge, which we're going to set to, this is, wait, what's my cast? Actually, we can set the cast write latency really low as well. MDI is just like really, really, really good. Well, actually, ADI also does this, but yeah, we should be able to set cast write latency very low. Which, like, it looks weird, but the sticks do it, so, or at least they should do it. We're going to find out if I'm an idiot or not very soon. 64. Actually, no, if we have it that low, we can go... Yeah, that should work. Actually, isn't there a power down disable somewhere? Yeah, so we want power down turned off. Basically, it's like a hot idle, like it's a idle state for the memory that I don't know why desktop platforms have, because it's like in a laptop it makes sense because you save a few fractions of a watt per memory rank by having the power down mode. And I guess in server applications it might also make no, server, well, no, it might make a bit of a difference in server applications if you have like a low power CPU but a ton of RAM. But yeah, in desktop applications, like I have literally no idea why it exists. Then we have a bunch of power down timings over here, which don't do anything, so we can set them very low. I can't remember what PPD does right now. Read to precharge we can set very low as well. Anything else? No. Latency timing, dynamic mode, and... should be a round trip latency timing somewhere. Where is it? Oh, round trip latency. Yeah, we enable this, and this will lower our memory latency a little bit. Or, like, improve our memory latency a little bit. On one hand, I kind of appreciate that MSI doesn't hide any of the memory settings. On the other hand, like, there's a bunch of settings here that you really don't have to worry about. Also, there's a bunch of settings that don't actually exist. Like, Intel CPUs do not have a TWR register. Just, like, straight up. They do not have a register for TWR. Your memory stick has a register for TWR, because if you use a auto precharge command, or write auto precharge, the memory stick needs to know the TWR timing for that. But I'm not entirely certain that Intel CPUs actually use those commands. So, you know, that makes that kind of fun. Oh, I didn't set TFAW to 16. CKE we can set to 4. It doesn't actually... okay, the board won't let us set it below the register limit. That's good. Yeah, like these timings also over here, these don't exist on Intel CPUs. Yeah. Anyway, so we're just gonna like we're gonna start with 6800, and then we're gonna bump it back up to 7200 afterwards. Okay, so it doesn't look like I made any massive mistakes in terms of timing settings. So now we're going to go back up to 7200. And hopefully it doesn't immediately fall over in Y-Cruncher VST. Though the issue is that with this CPU specifically, the way you would fix a lot of the Y-Cruncher instability is with the PLL voltages, which are really annoying to tune. If you have a 13900 KS, those don't tend to do anything, but with the regular Intel chips, the PLL voltages can help. Though maybe over time, like maybe some of the newer production CPUs don't need those, because this is like a launch CPU, because this is a CPU I got from Intel. Anyway, so here we are in Windows. I guess let's try first the Y-Cruncher benchmark. What? I'm very upset about something. Yeah, I didn't think that would do it. Same group? Oh, interesting. Kind of makes sense for Y-Cruncher, but yeah, surprising. I guess once you hit high enough speeds, it that time, because the thing is, most of my MDI experience is from like running it at less than 7,000 on like 12th gen Intel CPUs, or on Ryzen CPUs where you run it at like 6400 or less. And yeah, at those lower speeds, like you can run very, very low TRDSG. Okay, 12. I wonder if we can do 6 though, because that should work. It's not like it'll make too much of a performance difference. Run? Oh, yeah, it really seems to hate that. Or it hates the other adjustments I've made, but I think it's literally just the same group. That is very interesting. We could probably brute force that with more voltage, but there's really not much point in doing that, because the same group timing, like the memory controller really tries its best to not use it, so it doesn't tend to have a lot of performance impact. So if there's one timing that I'd be willing to sacrifice for stability, it's like, well, cast write latency, TRDSG, TRP, TRAS. That's sort of like the list of timings I wouldn't worry about too much. Okay, but I do wonder... TRCD, I think 40 is a bit too low, but like 42 might work, and then this might do 18. I might even be able to run lower RTP than 8. Because, well, at 7200, maybe not. Okay, we're gonna put the 48 back there. Oh, really? Let's try 56 then. So what write to precharge controls is the delay between the end of a... Well, actually, no, because it's the delay between a write command and a pre-charge command. And the main concern with it is if you send the pre-charge command too early, your write burst might not be finished yet. Though I don't think we're hitting that. Like, I don't... Actually, no. If we were in that scenario, the system literally wouldn't be able to run at all. Okay, well, in this case, I guess we're just going to go all the way to 64. This is really convenient, the being able to, like, test memory timings on the fly in the operating system. And the thing is, I'm not used to running MDI at clock speeds this high, so I'm not entirely sure where the timings will land. Like, right now, it really looks more ADI than MDI to me. Except for the TRFC. The TRFC is way too low for ADI. Huh, okay, no, it looks like it's upset about something else. Oh, it's probably the TRCD, actually. Yeah, because write to precharge, like, at least on most Hynix memory chips, can be done very, very quickly. Yeah, it was TRCD. So I think, like, the fact that, like, at 42 it won't even run Y-Cruncher, it's kind of making me think that even 43 is probably not going to be stable. Now, you might be able to fix it with more voltage, but TRCD doesn't really scale very much, so it might need a lot more voltage, and it might not get much lower. So I don't really see much point in, like, smashing voltage into this just to get TRCD, like, a tick or two lower than if we just leave it at 1.45 volts. Huh. But it also doesn't seem to like WR pre at 48, which I did not expect. I'm kind of wondering what latency we'd get in IDA right now. Oh. Well, it looks like 64. That is really loose, though, compared to what I've run on other memory kits. Oh, well. Yeah, these look okay. Oh, and yeah, TRFC per bank is set. So I guess let's quickly check what IDA looks like. $106, $110. Whoa, yeah, write is through the roof. I think $110. We shall consult the calculator because 7,200 times 128 divided by 8. Okay, no, I don't think we're violating the theoretical max bandwidth, but we might be, because I'm not sure. I think IDA uses gigabytes, not gigabytes. But anyway, 54 nanoseconds of latency, so not bad. Though the stability in Y-Cruncher is kind of annoying me. Also, like, this really should work at lower settings. And it's not linked to, like, TRCD or TRP. Well, actually, it could be linked to TRP, but not, like, loosening out TRP by 2 ticks shouldn't allow you to lower write to pre-charge by 16. Yeah, so it might just be TRCD being a constant issue. Anyway, I want to see what pi prime does now. And we're under 8 seconds now. Yeah, so massive uplift in pi prime, unsurprisingly. Kind of wondering if these two could go a bit lower, but we'll leave this the way it is right now. I mean, RTP might do 6, but it won't. Like, the thing is, like, read to pre-charge, this isn't generally a performance critical timing, because you shouldn't be rushing a pre-charge. Same goes for write to pre-charge over here. That one also is, like, not really that important, because it's used at the, like, end of a write transaction, not, like, to start anything. Though if you're rushing, well, no, I don't think, like, the thing is the memory controller really tries to avoid, well, like your SG timings, and a lot of scenario, like a well-implemented memory controller will basically try to pack the data into the memory so that it can avoid a lot of the really long timing delays, which would be anything that requires a pre-charge before you can do anything. So yeah. Anyway, they're pretty happy. Yeah, I'm relatively happy with these timings. Now the question is VST just going to immediately implode? Because it very well might. Well, it hasn't yet. And when I say immediately, I do mean immediately. Like this gets very upset very fast if you do something wrong. Kind of, yeah, I think these probably could be a little bit lower. Yeah, okay, so it is upset about something. But we're not going to try to... The thing with VST is, like... It's not necessarily upset about the timings at this point. And I know it also crashed at, like, 7466, and I didn't test it at 7200, if I remember correctly. Yeah, no, I didn't. Yeah, I don't think we've actually seen VST do a single full loop so far, so... Yeah, and this CPU has struggled to run 7200 in other motherboards in the past, so we're gonna quickly punch in the PLLs that... oh no, MSI does it. Oh no, they do it this way. They do them in absolute voltages instead of offsets. Anyway, these are voltages that I used on the Z790 Elite AX from Gigabyte, and they worked really well there with this CPU, so hopefully they work here. They should work, but... And actually, I think I used the exact same voltages or very similar voltages with the Z790 Dark at a much higher speed with A-die memory, so... yeah. That might actually just be necessary to get VST stable. It could also still be a timing issue. Oh, I forgot to fix the TRRDSG. Ugh. Actually, TRRDSG might clean up with the extra PLL voltages. The really, really annoying thing with memory overclocking is that you don't actually know what is causing the errors. Like, you don't know if it's because, like, you don't know if the error happened with the data, like, being written to the memory stick. You don't know if the error happened when the data was output from the memory stick. You don't know if the error happened when the memory controller sampled the data. You don't know if the error happened when the memory controller handed the data over to the system agent. You don't know if it got scrambled on the transition into the ring. Like, you just... Like, there's a very long chain between the data on the memory and the actual CPU cores, and anywhere in that chain, you could have an error. And when you get that error, you don't actually know where it came from. So, yeah, anyway, but we are going to bump up TRRDSG to 8. Open hardware info, and with any luck, VST will not immediately fall over now. It might also fail faster. Everything looks good so far. Yeah, now we get to the annoying part of memory overclocking where you run stress tests for hours and hours and hours, and especially with Intel's newest CPUs, you tend to get errors like towards the end of the stress test, not... Well, okay, no, that's not true. If you punch in really bad settings, VST will fail almost immediately, and that's nice. That's why I like VST. It's very good at telling you should give up right now. But as you start approaching, like, full stability, or, well, acceptable stability, you end up with the annoying issue of it takes longer and longer for the stress test to crash. And then there's also, well, I don't think at 7200 it's too much of a concern, but it is a concern with Intel memory controllers ever since 11th gen, actually. Because 11th gen introduced the Gear 2, and for whatever reason, Gear 2 has this issue of, like, sometimes it just boots up and it's not stable. And I don't know why that happens. And it usually happens when you're pushing the, like, motherboard and memory and the CPU really, really hard. Like, at low speeds, it's not an issue. At high speeds, it's a very real problem of, like, you can restart the system 5 times. Like, you can restart the system 3 times in a row and each time get, like, different amounts of stability without doing anything. Yeah, it looks like maybe just the PLLs alone might have been enough to clean this up. Now the annoying overclocker brain kicks in, and it's like, well, the PLL voltage is fixed 7200, so obviously what we need to do is go up to 7466. We're not doing that. Because again, we will bring up the calculator. 7466 is 4% faster than 7200. We are already absolutely destroying any XMP memory profile ever with the settings that we have here, and they're not even great. Like, we're at 1.45 volts, we're not mashing voltage into this. I didn't, lose considerable, like, well, yeah, like, this is... If this runs VST and then, like, test mem5 and HCI mem test, then it's, like, good enough. Like, I'd be happy with these settings. Like, I'd totally daily this. It's not going to get drastically faster if we push it higher. Like, we could blow the TREFI up. Like, we could probably set this all the way to, like, 200,000, but it's not really going to make too much of a difference. Because at this point, like, really, we are literally less than 1% of our available clock cycles are spent refreshing. And you could probably, well, no, because you're, like, yeah, if you lowered your TRCD and TCL, like, you could shave off maybe a few nanoseconds in IDA, but, like, it's not going to do anything. Like, it's not going to give you the same improvement. Like, most of the improvement with these settings really is just, like, the TREFI right there. Like, that's where most of your performance uplift comes with DDR5. You get a bit of extra bandwidth from your tertiary timings over here because, like, your read-to-read same group, this literally controls, like, back-to-back read operations. This controls back-to-back write operations. But again, write operations generally aren't that important because you don't... Like, there's a reason AMD's single CCD CPUs literally have half the write bandwidth of their read bandwidth, right? Like, write speed is just not that important. So, yeah. Like, really, write speed becomes, like, a concern if, like, you need to write something down before getting to read more stuff. But with with DDR5, like it's quad. You've got quad channel on the memory stick. Like the memory configuration is quad channel, right? Because you have 2 channels per memory stick, and so like you're not like if the memory controller is doing a good job, it shouldn't generally be too latency limited. Um, and so yeah, like RTP, like there's a bunch of timings that we just drastically reduced, but they don't actually change performance that much, which is kind of annoying. Anyway, at this point, it looks like VST might actually run. In which case, I've got like a nice, easy video done. But yeah, I think like hopefully this kind of illustrates my point. Like you don't need a high-end DDR5 kit to get like DDR5-7200 to run. Mostly what you need is a good motherboard and a good CPU, and then you need to know what voltages you need for the everything to work at. Um, and the memory kit, like if we had an A-die kit, we could probably run 7600 instead of 7200 with very similar timings, actually. Um, well, we would probably end up at like 36, 46, 46 instead of 34, 44, 44. But actually, well, if you shoved enough voltage into it, you could probably do CL32 at 7600. But the thing is, like, lowering your CAS latency by two ticks, just, it doesn't do very much. Because actually, like, yeah, here's an easy way to realize why it doesn't do very much, right? So CL34 and CL32, actually I should have done it the other way around. 32 is a 6% reduction in, and it's not even like read latency. This is read latency assuming that you already have the correct row active. So you get like a 6% reduction in read latency, which, like, not that important. Anyway, at this point, I will just let this run Ycringe for VST, and I mean, I guess I could try push it to 7466, but man, like the thing is, I don't want to. It's just like it's gonna be marginally faster, and it's gonna potentially take way more effort to stabilize potentially. And yeah, I don't feel like dealing with that. Anyway, yeah, that's it. So there. The MSI Z790i Edge is like very good with MDI, which I gotta say, like, I'm surprised because, like I mentioned, I did try these sticks a little bit on a different motherboard, and there they were stuck at like 7,000. Like it literally wouldn't even post with auto settings, which probably points to that motherboard just not being set up properly for Hynix MDI memory chips. But yeah, like thanks to that, I didn't have very high expectations for this video. So anyway, yeah, that's it. I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. So if you'd like to check that out, that would be much appreciated. And that's it. So thanks for watching, and goodbye.